The stream is about to start. We'll talk about code or whatever we'll talk about today. It's about to start, so please hang tight while I check that everything is okay. Sound check, camera check, lights check. How's my hair? Oh, wait, I don't have any hair. Maybe put some pants on and I am good to go. So get ready wherever you are, 'cause the stream is about to start. Get ready wherever you are, 'cause the stream is about to start. Hi, I'm Leandro Facchinetti, and let's write some code together, shall we? Shall we, Arya?
Let's do this.
Yes, let's write some code. How are you feeling, Arya?
You know, I've been better, but what are you gonna do, you know?
Well, hopefully the joy of writing code will cheer you up.
Yeah, I hope so too.
So, true to the spirit of the title of the stream, this is our pitch shifter. We have worked on this several sessions, and I don't really remember where we left it, and I don't really remember what is working and what is not working here. I think most things are not working right now because we were in the middle of changing lots of things. But how about we just dive in, see where we left off, and try to fix things along the way?
Sounds good.
Yeah. So I guess the main thing that we were doing was to use the library that I'm developing, because we started the pitch shifter just by writing everything the simplest way that could work, and we even started with a tutorial by Loser on the wiki, the REAPER wiki. And it has evolved a lot since then. And we left some notes of things that we know are not working. But I don't even know what grain wrapping even means.
Grain wrapping, I kind of don't remember either, yeah.
There you go. So let's see. We have the ratio, which I think that I don't really like the way that this works. We are probably not going to get to this now, but I think that instead we should have something in terms of cents.
Right, yeah. And also a ratio was broken last time. I think when we did like a ratio of 2, it was a major third instead of a fifth. And then 3 was an octave, weird stuff. So yeah, we should fix and then give it like semitone values, which is very interesting because I guess you gotta have a ratio to pitch relationship chart thing, because it's not gonna be linear, right? Like if you're going from a major third to a perfect fifth, you're going from a 5 to 4 to 3 to 2. And then the intervals in between are not in any logical order either. So that would be an interesting thing to tackle.
Yeah, I think that the way to go about this, not that we are going to do it now, but I think that the way to go about this is to go from cents and semitones into... Yeah, I think that there is a standard formula for going from cents and semitones to these fractions that you brought up, right? It's 2 to the power of the cents or semitones divided by 12. Isn't that the formula that one uses?
Maybe to my head, because we adjust the ratios for equal temperament, it's not a linear type of math. Like what you say will give us the true just intonation ratios, but we don't use those in Western music. So like our major third is a bit flat. So it's actually not a 5-to-4 ratio. It's like slightly, I think it's slightly sharper actually, our major third, than a real major third that you get from the formula.
Yeah, no. I think that the formula I am talking about, which is this one, so semitones, and if you wanted to do it in cents, you would just divide or multiply by 100. I think that this formula will give you, it will translate from semitones to ratios in a just intonation, not in an equal temperament way, not in a just intonation.
So like if we plug, say, 3 semitones in there, it will be 2 to the power of 0.25, right?
Yeah.
Which is what number?
It's this number.
1.18. And then you got to change this into a pitch ratio, or?
I think that this is the pitch ratio, because suppose, let's think about it just an octave. I said we would not be doing this, and here we are. But think about this as an octave. That's the ratio. 2.
Yeah.
Think about, well, unison. That's kind of boring, but still, it gets you right.
Mm-hmm.
And think about going...
Go 7. Yeah, okay, that makes sense. Because, yes, like a fifth has to be 1.5, but then we, like, adjust it a little. And then do 4. I'm wondering if it's... Because, yeah, so what this is very interesting. Because in Reaper, you have, like, you have actions to, like, adjust the play rate of an item to make it go up 1 semitone. And like the loose math of that is 6%, but 6% won't be perfectly in tune. So this is like that too, because it's like 2.5 or 0 or 1.259, which is a little more than 6% added together. So yeah, I think this formula makes sense. And I think that's how the equal temperament does it.
Yeah, I think that this does it right, because it's taking 1 octave and slicing it in 12 parts that are equally spaced on a logarithmic scale, because I am putting the semitones and exponent. And Lanterntronics, Aaron is here. Hello, Aaron. It's great to see you here.
Oh, yeah. I should check out the comment. Yeah, it makes sense.
Yeah, so since we have this conversation, do you want to just go ahead and do it? Because everything is broken anyway. What is the problem in breaking one more thing? So the pitch in semitones or cents? Or both?
I think like semitones, and then we have 2 decimal places, no? Or maybe actually 2 different sliders, so that if you are just adjusting semitones, it never goes microtonal. And if you want to go microtonal, you have a separate cent slider. Does that make sense?
Yeah, I agree with that. So the semitones one, and then another one for cents, and they're going to accumulate. So if you want to go 1.75, you can put this at 1 and this at 75. Okay, so this is going to be our pitch in semitones, and this is going to be in cents. In both cases, I think
start with nothing, yeah.
If you load the plugin, it doesn't do anything?
Yeah.
Okay. And we want to go down maybe 2 octaves.
Yeah.
It could be handy to have one for octaves while we are at it, because sometimes you just want to go 1 octave, and it's easier to just put a 1 here than to put a minus 12 here.
Yeah, true.
So how many octaves should we go?
Maybe let's go with 2. Most pitch shifters do 2, and if you want to do 4, you like load 2 of them.
Oh, well, let's
But
do
we can
4 then.
always... Let's do 4.
And this is naturally in octaves. And Aaron is saying, I have a student in my guitar amplification effects class working on JS effects for his final project. Awesome. I am learning C++, and I just love the feedback cycle of JS effects more and more. And I really like what you're doing there, Aaron, in your videos. You're sharing, if you all don't know this, Aaron is sharing videos of this course. I don't know if all the videos, but at least some of them. And they are very nice and very deep too. And Bo is here. Hello,
Very
Bo.
cool. Hi, Bo.
So, octaves. Do we capitalize this? I think we do, right?
Yeah.
And then uppercase. Okay, so it goes from -4 to 4 in steps of 1. Semitones goes from, I guess, -99 or -100.
No, you're doing cents.
Oh, yeah. So -11 or -12?
Yeah, -11 makes sense to me.
In steps of 1, and here -99.
Yeah.
No, you know what? You may be automating this, and in that case, you want to have the,
so
the
make
12.
it 12. And same, I guess, with this. Yeah, make go to 100.
But by default, they're all zeros, and then we do this. And maybe let's leave a gap between these parameters, so goes like this.
Makes sense.
And then we have on the slider block to compute the pitch ratio, which is 2 to the power of a bunch of things divided by 12. What is this bunch of things? This needs to be in terms of semitones. So,
is it pitch semitones plus pitch cents, basically?
Well, we have semitones, and that one is easy. And we will want to add stuff. We will want to add the cents, but we want to divide the cents by 100 because it's 100 cents that makes up one semitone. And we also want to add the octaves.
Plus 12 times 12, I guess.
You were right, I think.
Okay, this makes sense so far.
So there you go. Now,
The pitch ratio itself is right now broken too.
Well, the calculation of the pitch ratio is supposed to be right, but the use over here is broken. But let's load the plugin on the track and see if this number makes sense intuitively. And coming up is a great example of the feedback cycle that I love about JS effects, because we have here the variable pitch ratio, and right now it's 1. Oh, it's behind our faces. So right now it's 1, and that makes sense because we are not changing the pitch at all. Then if I go up 1 octave, it's supposed to be 2, and it is. And if I go down 1 octave, it's supposed to be a half, and it is.
Good.
Now, if I go up a perfect fifth, it's supposed to be around 0.5 or 1.5, and it is. And if I go, so another great thing about JS Effects is that the range of this slider is up to 100, but I can just type in any value and it will take it. So again, we are confirming that the formula is correct. And 1 semitone is about 6%, as Arya mentioned before.
Yeah.
So everything adds up. I think we did it.
Cool.
We came up with a cool formula all by ourselves. We didn't come up with the formula, but we reasoned our way.
Used it.
Yeah. And we did not have to look up on Wikipedia this time. No shame in doing that, though. Right, so what's next? We have the grain size in milliseconds and the crossfade in milliseconds. I think that makes sense, right? We are doing this pitch shifter based on the concept of accumulating some input into a circular buffer and replaying the circular buffer at a slower or faster speed to make the pitch go down or up. So this is maybe too low level of a parameter for a user because they may not understand the concept of how this works, but it's where we are at now. So this is the size of the circular buffer we are accumulating samples into, and this is how much we are going to crossfade when we reach the end of the buffer and need to wrap back around. Okay, so I think that in terms of parameters, I'm happy. Do you think there is anything you would like to change?
No, yeah, makes sense to me so far.
Okay. Then we are importing the library, and then on a init block, we are computing a bunch of things. Let's see. Oh, when we have this grain size, we want to have control over it. So we may want to expand or contract the grain size, which means that we have to pessimistically compute or pessimistically allocate the biggest grain that we could ever have, which is 1 second. So this is just 1 second converted into samples. It's supposed to be 48,000, and it seems to be. And then we are going to allocate several circular buffers, one per channel, because our pitch shifter is going to be multi-channel, at least stereo. And for this variable to exist, we need the serialize block, which is here, so that checks out. Then also this allocation seems okay. Looks okay to me. I'm just looping over the channels and putting stuff in the array. Then, when we use the pitch ratio, we are actually smoothing it out. So this is us initializing the thing so that we'll be able to smooth it out later. So we are controlling the rate of change. If you decide to go like this, and instantaneously the ratio is supposed to go from 1 to 0.06, we are actually going to ramp this over time. Okay. Then in the slider block, I am computing the pitch ratio with the formula we just derived, and I am translating from milliseconds into samples. I guess we don't even need that new line. And maybe this should be part of the library, right? Yeah.
Yeah, I mean, for pitch calculation at a later date.
Yeah. I think I will leave this as a to-do. So extract pitch to ratio into library. Then on the sample block, we are smoothing out that parameter that I mentioned before. And then we have this part. I guess this is where we left off because this looks messy. Yeah, this looks messy. So do we want to tackle this from the top or from the bottom?
On top, I guess.
Yeah, sure. So what is happening here is we have this read head position situation going on here, but I think that what's missing is, I guess this whole block here is stuff from the past. So one thing that is missing is simply pushing samples into the circular buffers. So how about we do that? Because that is a low-hanging fruit. That's easy to do. let's just put stuff in there. So I can say push a sample into the circular buffer. And Bo is asking you, Arya, if you have heard back from labs.
Nope, not yet.
Would you be interested in collaborating with them?
I mean, I don't have the technical know-how to do the fixes that I proposed, but if they want me to be like a user for them to like try stuff out on, yeah, I'll definitely be down for that.
That's the kind of collaboration I had in mind.
Yeah.
But you promised that you're the kind of programmer who couldn't do a search in 1 hour.
No, I never said that. I said a good programmer could. I didn't say I am one.
Oh, let me tell you. I am not a good programmer then, because it would take me more than 1 hour to do a search.
Or I don't know, like 2 hours or whatever. They got money. They have a search bar on their app, so they just gotta copy that code and then like change it a little bit maybe, but like they got the thing on their app.
Yeah. You make it sound so easy. I bet that their app is not written in C++, but the plugin probably has to be. So I think that their app is probably something like Electron. And doing a search in JavaScript, that I can do in 1 hour. But in C++, but it's also because I have much more experience with JavaScript than with C++. Right, so we're pushing samples into the circular buffer, but before we push samples into the circular buffer, we have to read stuff. And at some point, we will have some output. And then we want to produce this output. We want to output that output. So I'll do that as well. And this gets rid of this part. And also gets rid of these parts, because these were pushing into the circular buffer. So I guess in one way I am approaching it from the bottom. But it all started because of this line. So it is true that our read head needs to be independent of the write head of the circular buffer, right? And then let's tackle this. Let's tackle the notion of the read head. I will have a read index. Instead of head, I will call this the index, because otherwise it will clash with some name. Not, it won't clash, but everywhere else in the library, I have the notion of indices, like write index and read index, not write head and read head. So I'll rename this. And it can start at 0. Which is kind of redundant because every variable starts with 0 in JSFX, but it's nice to be explicit about this. So we have a read index there, and I will have a read index here in the sample block that I will update. So my read index will be equal to, let's use the circular counter. And the counter itself is the read index, and the maximum is the size of the grains. And naturally, we want to update this read index below, after everything has occurred. Then you know what? I just want to make sure that this part is working. So I guess I am going to comment out everything that is going on in the middle. And I just want to see this read index going around and never being greater than 100 milliseconds, which is 4,800 samples. So let's do that. Here is our read index, and it doesn't seem to be doing its thing.
Is it because no audio is coming, or? Oh, now something's happening.
Yeah, I just started the track. I just played, and it started going around, and it's never greater than 4,800. So it seems to have worked. Great.
Yeah.
And now, this gets rid of this, because no, I should not be just using this, because the read index should not be incrementing on steps of 1 every sample. In other words, it should not be going 1 sample at a time. It should take in account the pitch ratio, right? That's the whole point. So let's instead...
Say again, sorry.
Right now, the way that this code is written, the read index, of course I don't have a refresh rate on the screen to actually show this. I cannot see this number growing up in increments of 1, but it is being incremented 1 at a time. If I don't pass any step to the circular counter, by default the step is 1. So it means that on every sample, I am updating the read index by 1 sample. That is not what we want. We want the read index to be faster or slower.
Gotcha.
So for every sample, we may take a step that is larger than or smaller than 1. So we will instead use this version of the circular counter. And then the circular counter is the read index. The minimum is 0, and the maximum is the grain size. And then the step is the pitch ratio itself. Am I right?
The step.
The step is the increment. So by how much are we going to increment the read index on every sample? I guess if we want to play at twice the speed, we will increment the read index by 2 every time, right?
Okay, gotcha, yeah.
So this is the pitch ratio that we computed before.
And when we pitch down, what happens?
Then the pitch ratio will be something like a half. And in that case, we'll be updating the read index by 1/2 every time. So the read index starts at 0, then it goes 1/2, 1, 1.5, 2, 2.5, 3. And in fact, we should be able to see this in the little debugger. So right now, the read index is moving at 1 sample at a time. Same as before. But as I put this up, this now wraps up around much, much faster.
Faster, okay.
And as I bring this down, now this will be updating more slowly.
Still going pretty fast, actually. Don't you feel?
Maybe.
That's like, I don't know.
Now it's more slow.
Yeah.
More slowly. Interesting.
Oh, okay. So here's the thing. Maybe when our pitch ratio is a negative value, we are doing some multiplication or something that is getting rid of the negative value. So whether you go -4 or 4, we are making it faster. Does that make sense?
I don't think that's the case, Arya, because our pitch ratio is never negative. The ratio is never supposed to be negative.
Oh,
because
right. Yeah,
if the ratio was
yeah.
negative, we would start playing the tape backwards, which can be a cool effect.
Yeah.
But it's not what we are going for right now. And I think
it's just slowing
that
it
this
down.
is an optical illusion. I think that what's happening here is this is updating at audio rate. This read index is being updated 48,000 times a second. This number here is updated 3 times a second, maybe? Looks about 3 times a second. So what we are seeing here is aliasing, Arya. It's aliasing. Because this is not actually going from 1,000 to 2,000 to 3,000 as we see on the screen. No, it's actually going around the loop many, many times, and then we see 2,000. And then going around the loop many times, and we see 3,000. This is aliasing. Yeah, I think that this is what it is. I will proceed with confidence. I think that this is fine. So we have the read head position. We computed that. And there is some stuff here going on in terms of like buffer size minus crossfade samples. So yeah, we'll have to maybe revisit this when we get to the crossfading situation. But I don't know. Then this interpolation action, I think that our last stream was exactly about that. Yeah, we implemented in the library a way of interpolating. And I believe that this is working because there are some tests and they're passing. So I will not look at this and just take it for granted that interpolation is taken care of. So now let's try to use the library and implement this notion of going and grabbing the samples, but taking in account the grain and the interpolation. So what we will want to do is to get some sample from the circular buffer. So I guess I will have a circular buffer variable because we will want to use it here. And what is the index that we want for this? That's the hard question. Well, it must be based on the read index, that's for sure. But it also needs to be based on the write index to some extent. And it needs to be based on the grain size. I think I have an idea of how this could work out, but I'm not really sure. Okay, so the issue here is our circular buffer is very big. It's much larger than the grain. And every time we are pushing samples into the circular buffer, so the read head is advancing. The write head is advancing because we are pushing samples into the circular buffer, right? And I think that the grain, it should be following the write head. The grain should be the last 100 milliseconds that we have seen, the most recent 100 milliseconds. So as we write, the grain should be following the write head. And therefore, our read index, which is indexing on the grain, it's not a read index on the circular buffer, it's a read index into the grain.
Okay.
I think that this is how we can pull it off. So we have a function called get. It's this function. It takes as arguments a circular buffer, like the one we have, and an offset. An offset is a negative number and the offset is based on the right head. So if we say like -3, that's the right head -3. So in other words, it's 3 samples ago. So
Okay.
that is going to help us calculate the index we need, this notion of the offset. So we know that we don't want to index, well, we want something based on the read index, but we know that we don't want the read index into the circular buffer. We want the read index into the grain. So what is the base address of the grain? The base address of the grain is just minus, so it's the right head. This is implicit on this call to get. So the call to get is going to be based on the right head minus the grain size. That,
Okay.
so we have our right head. If we go 100 samples or 100 milliseconds worth of samples to the past, so that's why I have the negative here, because we're going into the past, that's where our grain starts.
Okay.
And then we are indexing into that. So we just say plus read index, and then we will have the index relative to the right head. So this function will just do its thing, and I think it will work.
Okay. I didn't fully get it, but I will in a second, I am assuming.
Well, if this logic is correct, this is supposed to be doing pitch shifting, but it's supposed to be clicking because we are not crossfading so far. We are taking interpolated samples, so it is not supposed to be too weird, but it's supposed to be clicking. But let's hear this, actually. Let's actually listen to the effect, because it stands a chance of kind of working, maybe.
And the clicks should be periodic, right? Should be like tick, 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 or whatever in time interval it is that we're collecting.
Yeah, they should be regular, and they should occur every 100 milliseconds, because that's how often we wrap around.
Yeah.
Yeah, I'm not sure that this is going to work, but I'm interested in listening to this. First, let's put some audio through this and see if it is doing something too loud. So what kind of audio do you want to play with? Do you want to play with an instrument, a sine wave, my voice?
Whatever you want.
Okay, I want to do your voice.
Okay. Hey, yo, how's it going? Forget about it. Hey, yo, whoa.
Yeah, I'm not even with the right routing here, so hanging there. Your voice is coming in from call output 1. And it is. Here is your voice. And your voice is kind of quiet today, so I will give you a volume boost.
Yeah, because I don't even have what I regularly have on my voice, because I can't open Reaper. Yay.
Yep.
Okay.
That should be good.
Hey, yo, forget about it. Okay.
Yeah, it doesn't seem like we are producing any loud noises. Let's try to do 1 octave up, because that's always more fun. And it doesn't seem like we're producing any loud noises, right? We are not clipping the signal anywhere. And did you remember to remove and re-add this on the track?
I think you did, but...
Now I did it again.
Yay.
So with that, let's add some hardware output to the computer 1 and 2. Yeah, all right.
There's some... Whoa! Hey, yo, how's it going? Yeah, I hear the click, and I hear the... Now the question is that 1 octave? Yes, it is 1 octave. Cool. Maybe do a 5th?
What is weird is that I zeroed this and it's still playing at a different
Yeah. So I think maybe you're feeding the pitch ratio into something, but it's not like updating. Is that what it is?
The pitch ratio is 1 right now, and the read index should be based on that. So there is something else that is wrong. But I don't know what it could be.
What if you change it now to a fifth?
Yeah, let's do that.
And just see if we fed like a new value. Does that do something?
Okay, so now it is 1.5. And do your thing, Ari.
It feels a little fat. It feels like a major third a little bit. Yeah, that feels a little major 30. So I don't know what's going on. It has a death. It just has a problem with fifths.
Yeah, I think that the root of the problem is in this formula, because if you didn't understand this formula, I did a bad job explaining it, and if I did a bad job explaining it, it's probably because I don't understand it all that well, which is probably because it's wrong. But before we try to fix it, let's try to do something that is supposed to be lower in pitch.
Cool. Maybe even reset the semitones? It didn't go up in octaves. Like it's not an octave lower or 3 octaves lower. It just feels like a slight adjustment of my voice, like the timbre changes, but the pitch change, if anything, would be like very small. I guess let's hear it. Maybe if I play a note, I can tell you what the pitch shift is right now.
Yeah, we could also just put a sine wave through, but I think I have an insight into why this may be wrong. When we are looking into the grain with the read index, we are doing that based on the write index, right? Because implicitly, as I mentioned, this get implicitly is putting the write index here. Right in this position, there is an implicit write index. So the write index is moving along. So if we want to just go one sample ahead, we should not be adding 1 here. We should just be adding 0, because the read index is going to be based on the write index anyway. So I think that we should do 1 minus the pitch ratio here. We want to increment this in steps of 0, actually, because then when we get here, will be... So if there is no pitch shifting going on, then the pitch ratio will be 1, and then we will be updating the read index in steps of 0. So we will not be updating the read index at all, which means that this will be 0, and this will be just minus the grain size. So it will be, I guess, 100 milliseconds worth of samples behind. It will be kind of a delay of 100 milliseconds, but whatever. And I think that this will do something closer to what we want. So do you want to play with a sine wave, or are you still happy with sounding like a duck? Okay, so first of all, say something, because I want to make sure that this is not producing any loud noises.
Hey, yo, oh, geez, oh boy.
It is producing loud noises. Interesting.
We're not even doing anything to like the signal, right? Like in terms of volume, we're just adding, like we're just speeding it up or slowing it down essentially. But that number now got wacky.
Yeah, this is producing a loud noise because the read index got out of bounds, which means that it is going to read into memory in any kind of location. It's going to read junk and produce junk as output. So that's why I wanted to test this first before I actually heard the result. So maybe the problem is that the circular counter is expecting implementation of the circular counter, I think, is expecting me to just wrap on the maximum, not to wrap on the minimum as well. So instead of using a circular counter, I will use wrap. And then wrap will need to be, what am I wrapping? I am wrapping a value with a minimum and a maximum. What is the value? The value is this. This is the value, this is the minimum, this is the maximum. So now this is supposed to be always in bounds. It's always supposed to be in the range of 0 up to that. Yeah. Okay.
I can't even play keyboard anymore. All right, wait.
Yeah. Okay, give me something. Okay, I fixed the bug. So let's hear what you sound like with this.
Now the 3 octaves was a fifth. Then it changed. See, all of these are not going down, they're going up.
Yeah, when I go negative, it's going up.
Yeah.
Fun stuff.
I have an idea.
Yeah.
Okay, so the formula that we use, the 2 to the power of something, is it possible that that's within the octave, and if you feed it a crazy number like 36, will it operate properly? Because it will be 36 divided by 12, which is 3. 2 to the power of 3 is 8. Oh no, that is correct. That is correct. So we're doing pitch octaves times 12. So if it's like -1, it would be -1 times 12, which is -12, plus 0 plus 0, then -12 divided by 100, 2 to the power of that, divided by, I can't do that math off the top of my head, but I think it should still work. Because even when we did -4 octaves, it was at 0.0625, which is correct for being 1/8 of the thing. So I don't know what's going on.
Me neither. Obviously. Yeah,
I have one more theory, and that is like, is our smoothing really slow, so we have to wait for it to go down?
That's a good theory. I will bring this down and wait for the pitch ratio to be small. It is small now.
Okay, yeah.
Yeah, go ahead.
That's almost unison. Or not unison.
Yeah, our pitch
like,
ratio is small, but this is going up in pitch.
Yeah.
So maybe my idea that I was supposed to be incrementing 1 here, maybe that idea is wrong.
Well, let's try it without read index minus pitch ratio. Should it not be read index times pitch ratio? I don't know.
Or maybe, I guess what I was going for, times the pitch ratio, you say?
No, maybe I'm being crazy.
No, I don't think so. Because if we wanted to play something twice as fast, we would be just taking the read index and incrementing it in steps of 2. So we are adding 2. We are not multiplying by 2.
Okay, yeah.
Yeah, and I think that what I explained before, the idea that I had in my mind was right, and I got the plus and minuses mixed up. Because what I want is for the read index to not update if the pitch ratio is 1, but I still want things to go in the right direction. I still want pitch ratio to be positive and... Yeah, I don't want to reverse the direction. So let's try this version now. I just swapped plus and minus here. So it will be, I guess, the read index plus the pitch ratio minus 1. And this minus 1... So this is what we had before I started with this idea. The purpose of this minus 1, I will explain again just to make sure that it makes sense, is to compensate for the fact that every time we push into the circular buffer, the right index is advancing, so the base address that we are reading into is advancing as well. So this minus 1 compensates for that. And now...
Oh, but here's my question. So then, in that case, if our pitch ratio is 1.5, in reality it would just be 0.5. Ooh.
We did it.
That was lower. Yeah.
Yeah, so what you're saying is that if our pitch ratio is 1.5, then the read index is 0.5, which means that for every sample here, we will be going ahead. We will be moving the read index 1 implicitly because of this and a half.
Oh, okay. Cool. Well, that also fixed it, so that makes sense.
Yeah. There is this phrase, I think it was by Donald Knuth, that he wrote some algorithm and said, yeah, I wrote the algorithm and I proved mathematically that it is correct, but I haven't really tested it yet. And this time we have not proven mathematically, but we have tested. It kind of works. So let's play around with this some more because it's so fun.
Sure. Yeah, that's a minus 1 octave.
There is a B somewhere in the stream.
This will be good also for... sorry.
Go ahead.
I heard my voicing. It would be good for like if you're making anonymous calls, just like modulate the hell out of the cents and then go down like 1 octave and be like, "Hello, I have your baby," kind of deal.
You know we are doing that now, right?
Yeah. I don't know if
is this fast enough for you?
Hello. I think that should be good. Hello, we have your baby. Give us all the monies.
And another thing that I want to point out is check this out. We are doing a lot of things. Right now, as we implemented, the plugin is actually multi-channel. So if we had multiple channels here, like a 5.1 situation, this would be handling that. And check this out, the CPU is not so bad.
Yeah. I did feel like when I said like a sentence, I noticed that. I don't know if you noticed it. It was as if some samples were being skipped.
And that, I think, is the case for sure, right? If we want to pitch shift up, then we will be skipping samples by definition because we are playing at a faster rate, so we'll be jumping ahead. But there is another thing, even if in this case we were an octave below, so we were not pitch shifting up. And even in that case, I think that as we are going in the grain from left to right, and we are about to wrap back, the grain itself has moved in time.
Yeah.
So if it has moved in time more than the grain size itself, we'll be not using some samples. We'll be just skipping them. But I guess this is a consequence of the algorithm we are using, right? I don't think that this is wrong. Or do you think it's wrong?
I mean, like on like a whammy bar, just as an example, this doesn't happen whether you pitch up or down. Like if you play something like super shreddy or whatever, it just sounds like that. But here it felt like the sentence that I said didn't get to the other side. It got to the other side with the correct pitch, but not all the info was preserved. So I don't know if they do something also. Because, I mean, you got to skip something, but do they have a way of, like, not skipping the transient? You know what I mean? And skipping the middle bit where pitch is affected? I don't know.
I don't know. I don't know if the whammy is even using this idea that we are using of taking rings and playing them faster or slower. But we could look into that. Maybe we would just lock the grain when we find a transient, or maybe they're doing something else entirely, because there are plenty of ways to do pitch shifting, from using FFTs to, well, plenty of things. So I don't know. But I think that just with our naive thing of taking grains and looping them, I think that it is the nature of the game. If we are pitch shifting down, we are playing things more slowly. So because time stays still, right? I mean, 1 second takes 1 second to pass. We are going to drop some blocks in the middle.
Yeah.
Yeah. But it gets too crazy, at least for me. I hear you, no, everyone, not just me. We all hear you twice, once dry and once wet. So I want to actually record this so that we can listen to it in isolation and see how good or bad it actually is. So to make this happen, I guess all you have to do is just say something.
Hello, we have your baby. If you don't send us the money, you're not gonna like it. I don't know what this is.
Hello, we have your baby. If you don't send us some money, you're not gonna like it.
You know what you sound like, Arya? You sound like a character. I don't remember which character, but you sound like a character from Banjo-Kazooie.
I was just thinking of the like Unreal tournament. The announcer was like combo kill. Kind of sound like that.
Can you give us a combo kill?
Sure. Combo kill.
Well, I guess maybe 1 octave is too much. Let's try that.
Combo kill.
Yeah, it is still skipping, but we can sort of make sense of what you're saying there.
Yeah.
Combo kill. Hello, we have your baby. If you don't send us the money, you're not gonna like it.
Here's my other thing I want you to try. No pitch of semitone or octave. I just want to hear the scent thing, just on its own. So 0 octaves and semitones, but keep that modulation going. Combo kill. Hello, we have your baby. If you don't send us the money, you're not gonna like it. It's definitely doing something that really makes it hard to like detect voice.
Yeah, and I do want to look at this pitch ratio smooth situation. It feels to me that this is not updating as fast as this.
Right, that's going really fast, yeah. Because we set the smoothing amount to like a number that just kind of made sense, right?
Yeah. and
Yeah.
we can change that number. When we are doing this smoothing, I think that by default, follower by default is this much, so I'll change the default, or I'll not use the default. And if we make it like this, it's going to move much faster. Let's see. I don't know, let's hear.
Hello, we have your baby. If you don't send us the money, we're gonna, you're not gonna like it. Combo kill. Sometimes it does feel like it sometimes goes up more than one semitone in some places. Very confusing. I also feel like maybe modulation is like throwing some extra unknowns in there. So maybe we shouldn't do the modulation before we do the other bits of the thing.
Fair point. But I'm glad that we got most of this working, and the code, I mean, so far, this is not crossfading, so it's not a fair comparison, but look at this. This is the plugin.
Yeah.
And there is some tricky business going on in the formulas and everything, but it's not terrible. And naturally, that was only possible because we are hiding some of the complexity here in the library. But that's the point. That's exactly the point of the library. Right. So, do you want to do the crossfading now, or do you want to wrap it up?
Up to you. I can go for a little longer. I mean, I honestly can't do anything else.
Oh, the issue of the dying computer. So yeah, let's do the crossfading then. So for the crossfade, we'll need to get 2 samples. And we'll need to check where we are in the read index situation, where we are in the grain. And then we may need to get another input. So first, let's check if we need to crossfade at all, if we are near the edges of the grain. And when I say that the grain is 100 milliseconds and the crossfade is 10 seconds, there are 2 possible interpretations, I think. I think that there are 2 possible interpretations. Interpretation number 1 is we have 100 milliseconds, and that's our grain. And then we have a fade of 100 milliseconds on each side. And it goes like this. And then there is interpretation number 2, that is, there is 100 milliseconds of crossfade, so it goes like this.
Yeah, to me, the crossfade, the way I interpret it is that the crossfade happens inside the grain size, doesn't add to the grain size.
So we are going to check, so suppose that this is 100 milliseconds, we are going to check if we are, another question is, if the crossfade is 100 milliseconds long, this area that I highlighted, is it 100 milliseconds? Because then we'll have 2 of them overlapping like this, or is it 50 milliseconds?
No, to me it's 50 milliseconds to my mind.
So it is going to consume 100 milliseconds, or it's going to consume, I guess, 10. It's going to consume 10 milliseconds of the grain, but it's going to be split by the left and right crossfades.
Yeah, and here's another thing, by the way. To me, like, what if we didn't give the user the crossfade and we just said the crossfade is 1/10 the size of the grain size? Because if you, like... Because I mean, well, obviously you can break it if the crossfade is like 1,000 milliseconds and the grain size is 100. But also maybe people wouldn't really need to even concern themselves with what's happening under the hood. You know what I mean? Like, here's the grain size and we'll figure out what to crossfade.
I like the idea of not giving control over that. I don't like the idea of making it... a proportion of the grain size. Because the purpose of the crossfade is to eliminate the clicks. So if you have a really long grain, I guess it works the same as here in Reaper. If I have a really long item, I don't need necessarily to make the crossfade longer.
A longer crossfade, right, yeah.
So we could just say that the crossfade is 10 milliseconds. And that's that.
Right, yeah. Yeah.
Okay. So we just remove this slider. And we look for cross-fading samples. And it's not based on the slider anymore. It is now a constant. And it is 10 milliseconds worth of samples.
Cool.
And I guess I disagree with you on something. I disagree with you that this should be, if our crossfade is 10 milliseconds, that this should be 5 milliseconds and this should be 5 milliseconds. I think that the length of the crossfade is this length here. This is how long the crossfade is going to take. It's going to take 10 milliseconds to crossfade from one to the other.
You know what? Yeah, I agree. Now that you put it in these visual terms, I agree.
Okay, so I'm of course splitting hairs because this is a constant and no one is going to see it anyway, but still. On the code, we'll have to reason about it this way. So now we have this situation. We have a grain. I don't like the color of this grain. I like it better now. So we have a grain and we need to detect if we are on the first 10 milliseconds or in the last 10 milliseconds of the grain.
Yeah.
And
we did this once in one of the earlier streams.
Yeah, that's what this code is doing somewhere in there. But I don't think it was working right. I think it actually had a bug in there. So I think it's worth rethinking about this. So actually, if we have a crossfade like this, then the length of our loop is this much. Right? Because when we get here, we start to crossfade. So
back to the start, yeah.
Yeah, so our read index should be looping up to there and then coming back around. And naturally, when the playhead is over here, we'll be taking some of these, but also some of that. We'll be looking at this position here and adding the two.
Yeah, so like before the read index is fully written, we're going back to the beginning already and starting to play it again.
Yeah, so now we have to change this read index because the read index so far is reaching the end of the grain. So far the read index is going up to here. We want to change the read index so that it goes up to there. That's what I'm about to do now. I will take the read index and we are adding the pH ratio and the maximum is this. The maximum should not be that. It should be the size of the grain minus one length of crossfade. So
but we're still gonna write to the rest of the buffer.
Yeah, the write index is independent of the read index. The write index is taken care of by this.
Okay, cool.
So now we are handling the read index correctly. We now have to detect, are we in this portion? Because if we are, it's a special case. We also need to come here and grab another sample. So let's see if we are in this portion. How do we tell? Well, we can come here and we can say, is the read index less than this? No, not that. Is it less than this? Right? Because the read index starts at 0 and goes up, and it's in samples, and goes up to here. If it is less than the crossfading samples, then we are in that special case. Am I right?
Yeah.
And now what do we want to do in that case? Well, we will want to take this output right now. This is the output. The output is, let's say, this sample here in the middle. We want to take this output and we want to attenuate its gain. So we will want to say that the new output is equal to the old one times some attenuation. That I don't know exactly what the attenuation is supposed to be. Or I guess I will want to do it like this. And then I will want to add this sample here, the corresponding sample on the right, which I don't know yet. I don't know what that sample will be. And I will want to attenuate that as well. And the attenuation here is going to be the opposite of that one because I want it to add up to 1. So it will be 1 minus attenuation. Does that make sense so far?
Yeah.
Okay. So now we have two things to take care of. Compute the attenuation and get the sample on the right. Let's start by computing the attenuation.
Also, another thing, I guess, another special case is the first time we're not looping, right? The first time we're reading the right head, we don't have the end to crossfade with.
It's
so
just a bunch of zeros. Let's
let...
crossfade with zeros and not worry about that case.
Okay, yeah.
Because it's just a split second anyway.
Yeah.
Or it is a split second. It is 10 milliseconds. So it will be fine. Let's not worry about it. And Aaron is saying that he loves this real-time pair programming. And we love that you are joining us on this ride. Yeah, so let's compute the attenuation with the simple thing which we know to be wrong because we tested before, but let's do a linear attenuation here because that's simple to implement. And so this starts at 0, goes up to there. So we just need to map the read index from a range that goes from 0 to crossfade samples into a range that goes from 0 to 1. Do you know this map function that I implemented?
No, but makes sense. You're taking like a table of values and you're corresponding them with like another.
Yeah, I am projecting this value from this range because that's the range that it lives in. If it is greater, then it will not reach here. So this is the range of the read index. And we are mapping this value from this range into this range. And because the base is always 0, there is actually a shorter and potentially faster way of doing this. I'll show you what it looks like, and then you can tell me which version you prefer. So you can just take this, divide by that, and that's that. So which version do you think is more expressive? This one or this one?
So you're taking a read index, you're dividing it by crossfade samples, and that gives us the attenuation. How?
So I guess you prefer the one on the right.
Yeah, because the one on the left, so that would just give us like 480. And then what are we doing with that number?
No, this is going to be a number. This number is going to be between 0 and 1. When the read index is 0, the result of this division is 0. When the read index is crossfading samples, well, I guess it's less than or equal in that case. But if it's less than, it's going to approach 1.
Gotcha.
So it's a special case of the map. I guess I will do it this way because it's faster. Map has to do a bit more arithmetic because in general, your range may not start with zeros. So
right, makes sense.
That's my attenuation. And now we need to get the sample on the right. So we need to compute this the index here. So it will be something similar to that. And then we are going to go back the grain size.
Yeah.
Or maybe not, because our right head is over here. We can just go back the crossfade length and then add the read index. So we don't go back the grain size in samples, we go back the crossfade length
and sample.
Plus read index, and that should do it. So now it should be crossfading linearly. And we heard this with a sine wave before and determined that this attenuation should not be linear, but never mind that. Let's hear what this sounds like, and hopefully it will not be clicking anymore. Oh yeah, I did not reload the plugin yet, so let's hear the old version to see if we can spot the clicks, and then I will load the new one.
Yeah.
Yeah, for me it is very clear that we hear the
Pretty
clicks.
obvious. Yeah, they're gone.
The clicks are gone, and I didn't even, I should have, but I did not even try this before listening. So we could have made a mistake and then it would have auto-muted. But it seems like we did it. Let's see. Let's try this, because this is going faster, so it will click faster if it is going to click at all.
Hello, we have your baby. If you don't send us some money, you're not gonna like it.
Am I crazy, or did it actually... It seems like less samples are being skipped or something. It feels like I understand more of the phrase now.
Well, it did have the effect of getting rid of the clicks, which helps with intelligibility, but also we made the grain slightly shorter, right? So maybe a shorter grain helps. Let's play with the grain size.
Yeah.
But when it's pitched up, I can clearly understand what you're saying. When it's pitched down, not so much.
It's a bit harder, yeah.
Hello, we have your baby. If you don't send us some money, you're not gonna like it. Hello, we have your baby. If you don't send us some money, you're not gonna like it.
Now see, with the grain size really small, nothing is being skipped.
Yeah.
It felt very smooth, and it just kind of like there's like a little maybe phase shift that was happening.
Interesting.
It just got like a little bit, like you could hear a tone change when you went from like 20 to 22 or something. You will probably hear like the tone change slightly.
Hello.
I'm hearing myself on a TV.
Ah, there is a there is a TV on the living room, and I think that they're watching the stream.
Oh, okay. Hi.
And I also hear myself coming back from you, so this stream is a lovely feedback cycle.
Hello. We have your baby. If you don't send us some money, you're not gonna like it. Hello, we have your baby.
Yeah, did you hear the tone change?
Some money, you're not gonna like it. Hello, we have your baby. If you don't send us some money, you're not gonna like it. Hello, we have your baby. If you don't send us.
Yeah, I hear what you're saying. I would not maybe characterize this as a phase change, because I wouldn't recognize a phase change if it slapped me in the face. But yeah, I hear the tone change that you're talking about.
You know, when the grain size is really small, it's almost exactly like the whammy. So can you try bringing the grain size all the way down and then play with the semitone, like go up like wee, like ramp up instead of just setting it to a value, like just move the slider.
Oh, and another thing is check the CPU cycle. It's much bigger now, probably because of the crossfades, because that's the only thing we changed. But we are indexing into the circular
does the
buffer
grain
more.
size also affect that? Like if the grain size is longer, there's less required, and if it's
Well, I suppose, because we'll check this, but I think that the only thing we changed since the last time I pointed out the CPU use was the crossfade. And the crossfade is making more reads into the circular buffer. And the smaller the grain size, the more we crossfade and the more we read into the circular buffer. So I think that a bigger grain size is supposed to bring the CPU use down.
some money, we're gonna
Yeah, I don't know. Anyway, 0.5% CPU is completely acceptable in my
it's
book.
fine, yeah. Yeah, totally. You're not gonna like it. Hello.
We have your baby. If you don't send us the money, you're not gonna like it. Hello.
Very nice. I like it.
I love this. It's so fun.
If you don't send us the money, you're not gonna like it.
And now, is it on this smaller grain? Can we make sense of what you're saying on a lower pitch?
Hello, we have your baby. If you don't send us the money,
Totally.
you're not gonna like it. Hello.
I think we need a new default. I think the default should be 20.
Pretty small, yeah.
Do you think that it should be maybe smaller? Do you want to play with smaller grain sizes?
I want to try that, but I also want to then try it with something musical, because okay, so I have the Isotope dynamic delay, which you can set the delay to be pitch shifted, and then you set a grain size. So on that, you have almost the opposite effect. When the grain size is very small, everything gets kind of fragmented and glitchy and grainy, you will hear the transient multiple times. And then when the window size is bigger, it's almost like you're hearing the same thing, just pitch shifted. So it's very interesting to me that here kind of the opposite is happening.
Yeah. I guess this is just a guess, okay? But maybe what they are doing is FFT pitch shifting. And in that case, I think what you're describing makes sense.
Mm-hmm. Because if the window size is smaller, you're actually getting less definition as well.
Yeah. And the FFT pitch shifting is a phase vocoder. For people who are interested, there is a chapter about this on Will Pirkel's book. And it's called the phase vocoder, the name of the chapter. And you do something very different from what we are doing. It has to do with FFTs. Yeah. It's very different from what we are doing. And then I guess the artifacts as well as the sonic results will be different. Maybe better, maybe worse, but different, that's for sure. Yeah, so let's play with a grain size of 15. Oh, and I don't know if you noticed, but I put a grain size of 10, and that glitched because it is the size of our crossfade. So we were probably trying to jump into memory that wasn't really in the circular buffer. But anything above 10 should be fine. So even 11 milliseconds should be acceptable. Let's hear this.
Hello, we have your baby. If you don't send us the money, you're not gonna like it.
I think 20, yeah, I think 20 is a safe place, actually. The pitch changed when you went to 15.
Yeah, 20 is a good value,
It
isn't
almost
it?
became polyphonic at 11. It was I was hearing two pitches.
Hello, we have your baby. If you don't send
There's
us
one here hello, and there's one real high. Very interesting.
Yeah. Probably at that point, we are starting to alias. Because we are going around the grain so fast. Because the grain is so small, we are going around the grain so fast that maybe we are aliasing. I don't know.
Yeah,
It's
maybe
weird.
we're creating a higher pitch that's whatever pitch is that the wavelength of it is 11 milliseconds. Or is it? And maybe that frequency will be present no matter what grain size we set. We're creating an extra frequency, which a lot of pitch shifters do. Like Whammy does do that. At 1 octave, you hear there is one frequency that like sometimes you can hear, sometimes you can't, but it's just a straight frequency.
Now we need to look this on with not a tone boosters, but a tone. Thank you, tone boosters, for making all your version 3 stuff free. Tone generator, and then spectrum analyzer, and wow.
Maybe let's make the tone a sine wave if it's not a sine wave already.
It is a sine wave.
Oh wow, we're doing crazy stuff to it.
Yep.
So if you turn off the, or yeah, do that. I think you're doing the right thing.
Yeah, let's see.
Okay.
Yeah, if the grain is 20, then we are not making crazy things happen. But if our grain is smaller, then interesting. Oh, I guess it's because I'm not doing any kind of shifting. But as soon as I start doing pitch shifting, yeah, it's creating a bunch of harmonics.
So, what if you set it to 20 now? Will they go away, or
I
will
hope.
some of them stay?
Yeah.
They went away a great deal, but there is some audible like action. Ooh, very interesting. So, what if you set the grain size to like 200? I'm wondering. Wow,
No, do you know what is
that's
crazy
nuts.
about this? What is the frequency that I'm putting through this? Let's put a frequency that makes sense, like 1,000. Not 100, 1,000. Thank you. Oh, then it doesn't happen. Okay. So let's do 100, whatever. But it's creating
Double pitches,
1K,
yeah.
2K, 3K, 4K. So this is a square wave, isn't it? No, a
But
sawtooth.
what is interesting is that it also has a double peak. Do you see the harmonics?
Yeah, I do. But it seems like this is just good old distortion. But what is crazy about this is that it's not aliasing. It's not coming back down.
Yeah.
Or maybe it is, and that's the second peak that we see. Let's take this frequency in fine-tune sense and modulate that to see the dancing. Yeah, it's aliasing.
Yeah. One goes up, one comes down.
Yep.
Q.
Okay, so that's settled. I thought we had just ran into a technique for kind of distortion without aliasing, without oversampling. But of course not, because you cannot have your cake and eat it too. So, yeah, let's not modulate this. And coming back here, let's make the grain size of bigger, because you said that if it's 200, then the distortion should go away. And it does.
Okay, cool. And oh wait, go back to pitch octaves being 1. There is I saw what I felt like was a creeping like 10K tone at one moment. No, but yeah, it's very oh yeah, did you see it when you went down to like -3 or -2? Yeah, you see it? There's a 10K thing when you're at -2.
I see it, yeah. When I am at -2 precisely? Yeah, exactly. There you go. Let's
Yeah.
make this lower and then check this out. This is aliasing, I think. I think it's this peak reflecting back.
Possible.
Yeah, I can make it dance, see?
Ooh, very nice.
Yep. Cool stuff. All right.
So they do. So I think also another thing that happens is like our 20 millisecond grain size Like maybe in some other octaves there will be another value that would work better. I don't know.
Oh, fair. Yeah, but I think that we did the right thing calibrating this with our or your voice, because it's going to be the range that we probably going to care about the most. Most people are pitch shifting guitars, voices, that kind of thing. But yeah, you do make a good point. Yeah, this grain size, it is going to have different effects on different frequencies. So I suppose that the higher the frequency, the lower the frequency, the bigger grain size we'll need, right?
That's how it works on that D delay, on the isotope delay that I was talking about.
Yeah, and it makes sense on whatever kind of pitch shifting that you will do, I guess. If you want to play with lower pitched sounds, you want your grain size to be larger because you want to be able to capture that waveform to pitch shift it effectively. Right. Okay. This is great. This is doing something.
Yeah.
And I guess the solution for aliasing, because we are running into issues with aliasing, it could be just oversample. Oversample 8 times. You're good to go.
Bob's your uncle, yeah.
And I guess oversampling will also affect the grain size, right? If you are oversampling, your grain size will be... a grain size of 20 milliseconds is going to be much more samples. We will have much more samples in that space. So our crossfade can be smaller and other things may occur.
Somebody's knocking on my door, BRB.
Okay. And while Arya is away, he tells me that I am an over-deleter. And I guess I am, because I think that we are good to delete this. I don't think there's anything in here that we didn't implement. So that's that. Pitch shifter in 57 lines of code. Isn't that amazing? Oh, most of them are comments and stuff. So in 50 lines of code, let's say. I'm happy doing that. I hope Arya doesn't see this.
All right.
Arya, I just deleted the whole block of code that we had before. Do you think that there was anything in there that we are missing?
We did the crossfade action. With smoothing, is that? Yeah, smoothing is there. Yeah, probably all right.
Yeah, so let's come back to this grain wrapping. I don't know what that is, so I'm removing it. Crossfade with equal power instead of equal amplitude. That's who I think needs to be done, and this also probably needs to be done as well. But do you want to try to do this now, or do you want to just call it a day?
I honestly feel like when it comes to really short crossfades, which 10 milliseconds is very short, like equal power and equal amplitude, the difference isn't audible. It's only with longer crossfades that I personally like hear a difference between those things. But what would be kind of fun to try is like, yeah, I wanted to basically do the same thing. I was gonna say like print a sine wave, but yeah, also with this, like seeing what happens at the edges.
Yeah, so right now no action is happening on our pitch shifter, and Tail is here. Hello, it's great to have you here, and I am glad that you are finding this entertaining. And yeah, I was pointing out, Arya, while you were away, that this whole thing, I will remove these to-dos here.
Cool.
I will put them here, pitch, shifter. And the reason why I'm doing that is to point out that this whole implementation is about 50 lines of code. using the
Nice.
library, of course. We are using the library heavily here. Most of the interesting things like interpolation are happening in the library. But still, if my library is done correctly, then you're supposed to pull these kinds of things out rather easily. And it is, I think we can claim to be the first multi-channel pitch shifter. I don't think that any other pitch shifter is multi-channel. So now if you want to do your Atmos stuff with pitch shifters, you can with a single track. Right, but we were looking at the crossfade to see if it was jumping up and down in gain. So with a really short size, we should not be seeing any kind of artifacts, and we are not. But if I make this longer, we are still not seeing anything.
But we're not pitch shifting. Maybe we need to also pitch
yeah,
shift.
good point. How about we play an octave above? And then we see it dipping.
Yeah.
And I was doing some reading because I'll be honest, when you said that the issue was probably equal gain versus equal power, I had no idea what that was, but I pretended that I did. And then after the stream, I looked it up and I learned that it is two different ways of crossfading. I think that the terminology comes from Pro Tools. And what I learned is that there is no one that is better than the other. They do different things. So one, I don't remember which, is supposed to be better for when the signals are phase coherent, and the other, I don't remember which, is supposed to be better for when the signals are not phase coherent. I don't remember which is which, but in our case, can we make any kind of assumption about the coherence of the phase?
Well, so that would also relate to our source material, right? So for example, say our grain size is 100 milliseconds and we're going up one octave, but our base frequency is 110 or our wavelength of our frequency is 110 milliseconds. So in that case, wouldn't it be that every time we wrap around, we are arriving at another place in the cycle of the sound?
That is true.
And to talk about the thing that you were saying, I never like heard it relating to phase. But like one thing I do know is like they always told us like, if you are, like if you're making like a seamless loop and you want to wrap back to the original place that you're wrapping back to, always use equal power instead of equal gain. So maybe they never told us why, but maybe this has to do with that so that you don't like mess up the phase. Because if you do equal gain in that case, maybe you're affecting the phase.
Interesting. So, in other words, you are saying that we should be doing equal power, not equal gain, right?
Mm-hmm.
And as far as I understand, this is what we are doing. We are doing equal gain. So we are just ramping this up between 0 and 1 linearly. And this is equal power. Yeah. The relation should be this curve, right?
Mm-hmm.
So now the question becomes, how can we compute this curve? And in particular, the kind of need that we have here is exactly on this line. And we have a value between 0 and 1, so that helps. We just need to compute this curve, and we need to be able to compute arbitrary points in the curve. So maybe one way of doing equal power would be to just start at 1 and then multiply by 0.01 over and over and over again. That will not cut it. We'll have to compute, like, I want in this point, right here, where my cursor is, what is the value there?
Yeah.
And do you happen to know the formula for this, or even the kind of keyword that we would need to search?
Does it not look like 1/2 of the function for y equals x squared upside down? Does it not look like that to you?
It could be. It could be. It could be the right-hand half of minus x squared, right?
Yeah. Aaron is also saying what I also thought. Like, yeah, I don't understand how it would relate to phase, because we are not changing the direction of any waves. We're just kind of multiplying them as the phase is happening. Yeah, I just know that like whenever it's short, it's almost impossible to feel the difference. And if you do like a 2-second crossfade between like two pieces of music, you will definitely feel that when it's equal gain, near the center, you are feeling a drop in loudness because both songs are playing at half loudness. And then so you hear like a reduction in volume and up. But when you do equal gain, the middle point where they intersect happens when they're at about like 0.8 the loudness, and then it goes down, so you never feel that difference. I always thought it has to do with like where the point of intersection, moving it up so that we don't feel a gain change.
Yeah, and the gain change is exactly the problem that we can see here on the oscilloscope.
Yeah.
This gain change is what we are talking about. And
how many dB is it? It should be 6, right?
Well, to answer that, I can simply look at... I'm trying to find a zoom that is going to help me read this out. So it is at minus 12 at the peak, and over here it's at minus 15. So it's a difference
15.
of 3.
Okay, so it's a quarter, yeah. Or sorry, not a half, it's a 0.75.
Yeah, I guess. So... I don't
and that
know.
makes sense because it's both sides half loudness. So if it was one side, it would be minus 6. Since it's twice, it's minus 3 dB.
Yeah. The problem is just I don't know what formula to use for this, and I don't even know what to look for, but I think that people will just give me the answer in the chat, hopefully. Yeah, I think that they are doing exactly that.
Tail, I think, gave you the formula.
Yep. Adding 2 identical signals gives us plus 6 dB, and adding 2 incoherent signals gives approximately 3 dB when correlation is 0.5. And for equal power, I think you can crossfade with that, where x is... we already have x between 0 and 1, so I'll just plug the formula you gave me. And I don't need both of them, I just need one, because I am just computing the one on the right based on the one on the left. And they need to be complementary. So right now, this value here is your x between 0 and 1. Let's just take this. And paste there. And in JS Effects, pi is spelled with a $sign. And let's see if I need the sine or the cosine version. When the attenuation, when the read index is 0, I am right here and I want the attenuation to be 0. So I want the, so this is going to be multiplied by 0. So this is going to be the cosine of 0. The cosine of 0 is 1.
1, isn't it? Yeah.
So I want the sine version. Yeah, Tail was giving us both versions with... Oh, hang on. No.
Should it fade out cosine, fade in sine? Is that what should happen? So at the end of the grain, at the beginning of the crossfade down from the end of the grain size, we need to use the sine so that it starts at 1, ends at 0. And then when we're starting from the beginning of the grain to crossfade up, to fade in, we need to use cosine so it starts at 0 and goes to 1.
Yeah, what my understanding of what Tail was saying and my understanding of what you are saying is that you would use 1, either cosine or sine on this side, and either cosine or sine on this side. But my claim is that we only need to compute this one on the left, because the one on the right is just 1 minus the one
The
on the left.
opposite of that. Right, makes sense.
So we just need this one. And right now with sine, it is going to start at 0. And when this is 1, the read index is 1, then we will be multiplying by... Not the read index is 1. This division is 1. When this division is 1, we are multiplying by pi over 2, and the sine of 90 degrees is 1. So there you go. I think that this does it. And also Tail was helpfully giving me the approximation that is cheaper to compute, because
Nice.
sine is an expensive thing to compute. But before I even try to optimize this, I want to see, and thanks for helping me out here, because I have never done a crossfade before and I didn't know the formula for it. But now that I explain it, it kind of makes sense. Right, so let's remove this and stop the hold. So now the waveform looks like that. And then let's pitch shift up 1 octave and put everything in the oscilloscope. And would you look at that? This is interesting, isn't it?
So now bring up the grain size, because what's happening now is that our crossfade size is just half our grain size. So in a bigger thing, now it feels pretty like we can't really exactly pinpoint where the fades are happening.
Yep. I love it. Thank you, Tail. And because I want to learn, I will also try your approximation. And I want to see what that looks like. 1 minus x squared and 2x minus x squared. Would that be for the one on the right? I don't know. So this is our x. I will put it there. And then let's reason about this. When the read index is 0, this is going to be 0 squared, so it's going to be an attenuation of 1. That's not what I want. I want the opposite of that. So I guess it goes like this. So when the read index is 0, this is going to be 0. When it's 1, it is going to be 1, but it's going to be power because it's squared. So simple. You just take the linear thing and you square it. Of course, because that's power. You take the amplitude and you square it, and that's power.
Yeah.
So simple. I love it.
Nice. You know, they said in school, my high school buddies were like, don't study trigonometry, you won't use it in real life. Smoke weed. And now look at us. Or look at me, you know.
You're throwing me under the bus
weed.
here.
Yeah, you probably just studied trigonometry, but I chose weed.
Did I do everything right? Because it seems like it is fine. Oh, I didn't pitch shift. Okay, now it's crazy. And now it looks wrong.
Can we freeze it at the intersection? I just want to know how many deebs.
A lot.
A lot of deebs? Yeah, that's like 15 to 24. That's like 9-ish deebs.
Yep. Interesting, but it looks correct.
And Tail's saying not x to the power of 2 because the curve is upside down. Or x squared, I should say, not to the power of 2, like a nerd. Like a noob.
Ah. I think I see that. Yeah, we want this coefficient to be negative because we want the curve to be... Hang on, do we? Yes, we want the curve to be down like this. So how do I even think about this? I guess I just take... I guess we need to return to the 1 minus situation, but we want the read index to be negative, I think. I don't know. I'm having the hardest time thinking about these things. I always have the hardest time thinking about these things. But I do like this notion of just squaring things because it's much more straightforward without using sign. Besides being faster, it's also more straightforward once I can reason about the indices and everything. So let's see, what do I need to make this happen? You know what? I need a graphic library to help me think. Unless you all have the answer and I'm making a fool of myself. In that case, then just let me know. But right now what we have is minus x squared. Like this. And I want a number to go between 0 and 1 on that shape that we have here in Reaper. Oh, I think that tail is giving me the answer. Oh, so that was the answer all along.
Okay, 2 to the power of x, yeah.
Thank you.
Beautiful.
You are the best.
Very nice.
Yeah, that was the answer that I just didn't pay attention to there. Silly me. No, not that. This. And I guess there is a better name for X here, right? This is
the thing that we plugged in.
Yeah.
Read.
But it is the
Crossfade amount?
It is the attenuation in equal gain, while this is the attenuation in equal power. And this for sure is something that I want to include in the library, so I will take note of that as well. Equal gain versus equal power. Because this is the sort of formula that if it lives in the library, then people won't have to think and won't have to call tail. Yeah, interesting.
Noise.
But of course, we want to make this. Hang on, we didn't even have to increase the grain size this time. It is a bit crazy, of course, but it's not as crazy as it was before with the sign, the sign version.
What is the frequency of our tone? I'm wondering if a slight phase shift is occurring, because it's 218. So it's not like a regular, so it ends up at the cycle in irregular places. So right at that moment, it feels like it's shifting a little bit, which is, I mean, that's inevitable if you have any kind of frequency. Yeah, you see that? Mm-hmm. Right there? Yeah.
And that explains
so
the harmonics that we saw. It also explains...
Yeah.
Yeah, but... Hang on, aren't we crossfading? This was supposed to be smoothed out more than I think it is.
So I think though at the point where the crossfade is about to end, now we're doing less of it, right? Because at that point the squared values are essentially like equal. Does that make sense?
It does not to me, no. It does, for me it seems like it is not even trying to crossfade here.
It does look, yeah, it does look like in one sample we just jumped to another point of the action. You're right.
If this was crossfading, then I was expecting the waveform to be squished here because its target is to get there, so it was supposed to be getting squished here and then moving there more gradually.
I'm wondering if increasing the grain size will, well, it will change this, but I'm wondering how it will change this.
I'll stop holding and increase the grain size.
Yeah. Oh, the grain size is actually pretty high. I see. Okay, I thought it was still at 20. Well, now I want to know, yeah, what it looks like at 20.
it's. I think what's happening is the same
still
thing. It's
doing
just
that.
happening more often.
Yeah, it's still doing that. And look, it's okay. We know that it wasn't ever going to be the same because now it's not. That is interesting. So what happened there? Yeah, something happened there, right?
This curve does look right though. What is it
Yeah.
compared to the other formula we used, which again I am just going to sheepishly copy and paste, where pi is, how do I say pi here? Oh, that's how I say it. And
How
I wanted,
did you say it?
I just wrote pi and it converted. But when you copy and paste, it doesn't do that.
Yeah, that's like very hard to even tell the different stuff.
Yeah. And it's interesting. What Taylor was saying is that the blue one, the sign is the correct and the red is the approximation. But it seems to me like if we're talking about gain and power, this is supposed to be the correct one, isn't it? Because this is more like power. It's squaring things.
Right. And I mean, the important thing is like if those two intersected, they would both kind of intersect at around 0.75, which is kind of what we want. Right, so if we cut the thing from the point of x equals 1 and just move that bit over here, when they intersect will be at around x equals 0.5, which is like y at that point is 0.7, and then it's like 0.72 on the other one, which is how it needs to be. I mean, either way, it would be so tough to hear the difference between these two, so I think going with the approximation is totally like a winning idea.
Yeah, you're right. So if we look at the blue one, it is the correct one. So there is more to power that I need to learn actually, because this is the correct one. At half, it should be 0.707, right?
Mm-hmm.
It feels to me. While here we just have 0.75.
But 75 seems to me like the right answer. Because that means that if you get two equal loudness things, in the middle of the crossfade, you will have no change in overall loudness. Because they will be both minus 3 dB, and then you sum them together and you get to
But
where
the thing
you
is,
are.
minus 3 dB is not 0.75.
Isn't it?
No? Minus 3 dB.
6 dB is half as loud, so 3 dB is 3/4 as loud?
No. 3 dB is 0.707. I don't know. Let me now check because I am getting confused. But the log 10 of minus 3. No, not the log of minus 3. What am I doing? 10 to the power of minus 3 divided by 20 is this. So that's minus 3.
Okay, cool.
That's minus 3.
Cool.
So yeah, Tail, you know your maths. This is the
Nice.
correct curve. But yeah, this red curve is a good approximation, and I don't really understand why it doesn't look like it's crossfading anymore.
Yeah, I guess the
It's because I am a
3dB, 60
silly person. That's why.
You're double attenuating.
No, it
I
was
guess
just a
the,
silly mistake in the code, okay? We can all calm down. That is 5 minutes. That is never gonna come back.
Pitch shift.
Now this looks about right. And now this looks about the same thing we had with the sine formula. And as we make the
Can
grain
you
size
hold
bigger.
And zoom in.
I can kind of see the
I see a thing.
yeah, it's moving around. Let me try to catch that. here, I got one. I'm zooming in. Let's see. I claim that this is not something you can hear. So this approximation makes things faster because we are not computing the sine, we are computing a square. And we saw the difference here on the graph. So I claim that this is good. But I also need to copy and paste the comments from Taylor.
I guess when they say 6 dB is half or 75 is 3, it's like an approximation for ease of math. But
oh, absolutely,
reality,
yeah.
like,
when you say that -6 is half, it's actually this.
Yeah.
And -3...
It's good enough for government work.
Yeah, and that's, I think, related to the Q in equalizers, because the Q, when you want no ripple, is exactly this. And it is related to things like 1 divided by the square root of 2, which happens to be this value as well. Lots of interesting things going on there, but I don't know enough to talk about it. Oh, yeah, well, seems like Aaron knows about it. Oh, man, I feel silly. All right. So now this is the equal gain. This is the equal power, approximated, not really, but approximation. And with that, I need to do the following things. I need to bypass these guys. I will drop the effect back in for one last time because I may have changed something about the source code. I don't remember. And Arya, do you want to say goodbye like
Sure.
do you want to say goodbye like a duck, or do you want to say goodbye like you're trying to steal someone's money?
Let's do -1 octaves.
Okay, we'll do that. And now it's on. So Arya, thank you very much for joining me on this. It has been a lot of fun, and I guess the next time we meet is for audio production stuff, right?
Mm-hmm. Friday.
Okay, on Friday.
Have the money. Unmarked bills.
So on Friday, we are going to do some audio production stuff. We haven't decided exactly on what yet, but that's what's coming up. Tomorrow, I will be back here, and I will be back to waveform drawing. I think I had a breakthrough. I think I have an insight on how to fix that whole situation that we have going on with the screen kind of, the waveform kind of flickering around. So look forward for tomorrow's stream in which I will be trying to implement that idea. Thank you all who helped me along the way here. Theo and Bo and Aaron, you're all great. And I look forward to seeing you again here tomorrow. And yeah, go watch Arya's video, his latest video on his channel about the Labs plugin. It is his best video of all times, according to me. But I think other people as well.
Goodbye.
Thank you for watching the stream, you know how great it has been. Or maybe it sucked, and I am glad that you stuck with me. And soon we'll all be back together for some more coding or talking or chilling. The next time I'll be streaming.